What's under the hood? Understanding the internal workings of the American Highway Dowel Optimizer provides valuable insight into how this tool closes long-standing knowledge gaps in dowel design. For decades, engineers have relied on simplified assumptions and conservative approximations to address design challenges related to modulus of dowel support, load distribution, and load deflection. This video breaks down how recent advancements in research modeling and computational tools have allowed the Dowel Optimizer to resolve these challenges with modern precision. First, resolving the modulus of dowel support. One of the most persistent questions in dowel design relates to the modulus of dowel support, a parameter long assumed to be 1.5 million psi per inch. This estimate was widely accepted in part due to its inclusion in concrete pavement textbooks where it was considered an insensitive input. However, this generalization fails to account for dowel shape and other factors. Recent PhD research at the University of Illinois addressed this issue for tapered plate dowels, validating predictive models with physical testing and finite element analysis. These models demonstrated that the modulus of dowel support isn't a fixed value, but rather varies with dowel geometry, slab thickness, and installation conditions. The Dowel Optimizer incorporates these findings to calculate the modulus of dowel support for all dowel types with improved accuracy. Next, considering load footprint in design. Historically, engineers have assumed a concentrated point load for dowel group analysis, an unrealistic but conservative simplification. This model fails to reflect real-world loading, where tires and wheels have a measurable footprint that affects the load distribution across dowels. Using examples with 5,000-pound wheel loads on an 8-inch slab, the Dowel Optimizer shows that as the dowel spacing increases, the load on each dowel increases, though non-linearly. Moreover, when the contact area of the tire is considered, ranging from small hard wheels on pallet lift trucks to large pneumatic tires, the resulting dowel load decreases significantly. In the most extreme case, assuming realistic tire size led to a 50% reduction in the maximum dowel load versus a concentrated load. These outcomes highlight the importance of load footprint dimensions in dowel design and are fully accounted for in the tool. Number 3, quantifying deflection between dowels. The third common critique of prior efforts involves deflection between dowels, particularly when dowels are spaced further apart. Prior to this tool, no widely accepted model existed to quantify this behavior. The Dowel Optimizer's development team employed AI to generate a new mechanistic model based on existing research and selected publications. This model shows that deflection between dowels increases with dowel spacing and decreases with a thicker slab or a higher elastic modulus of the concrete. For instance, a 5,000-pound load on a 6-inch thick slab with dowels at 30-inch spacing can yield almost 0.02 of an inch of additional deflection. That's nearly 20% of a typical design limit of 0.010 of an inch. The model was validated with finite element analyses and provides a robust solution to an issue that has previously lacked quantifiable answers. Lastly, addressing joint construction tolerance and other refinements. Beyond these core improvements, the Dowel Optimizer also accounts for joint construction tolerance, often a source of real-world dowel performance issues. For standard users, a default tolerance of plus or minus 3 inches is applied to all dowel types except diamond and rectangular shaped dowels. These two are assigned a much smaller tolerance of plus or minus 0.3 inches. Advanced users can modify these values as needed. Additionally, a dowel looseness model adapted from earlier work by Walker and Holland is included until further field data becomes available. The Dowel Optimizer references studies from a broad array of institutions including the Federal Highway Administration, several universities, the Transportation Research Board, and the American Concrete Institute, all of which are cited in the Comprehensive References section. In summary, the American Highway Dowel Optimizer represents a major advancement in pavement and slab design by directly addressing long-standing engineering critiques with validated models, modern computational tools, and empirical testing. By refining inputs like the modulus of dowel support, accounting for realistic load footprints, quantifying inter-dowel deflections, and integrating construction tolerances, the tool gives engineers the confidence to move beyond assumptions and design with precision. This is what's truly under the hood of the Dowel Optimizer, a data-driven foundation to support the future of pavement and slab engineering.